All right, gentle people, let's go ahead and cover sections 15.2 and 15.3. So last we were talking about rate. And so what we want to talk about is how fast a process is occurring and what are the factors that impact that rate. And so we're going to still stick in with this simple reaction, A going to B, where A is my reactants and B is my products. Now, last time I mentioned to you guys that we can describe rate in either in terms of reactants or in terms of products. Now, I'll let you guys know about 90% of the time, people are going to reference rate in reference to the products. So that's what I'm going to do here. I'm going to describe rate as a change in my products versus my time. Now, if it is the change in my products, remember this is the change in concentration, and concentration is measured in molarity. Time measured in seconds. And so what we have here is that rate is going to have the units of moles per liter per second. Now, if you guys think about this, this can also be molarity per second. So that's going to be the units of rates, and that is going to be consistent. Now what we're going to do is we are going to go ahead and describe the rate in terms of the concentrations of our reactants. So remember the factors that impact rate. One of them is concentration. And so what I'm going to do is say to you guys that the rate is dependent on the concentration of my reactants, and I don't know how it is affected by that concentration. And so I'm going to raise that concentration to the nth power, and I know there's a proportional relationship between concentration and the rate of my reaction. Now, I'm going to describe this in terms of an equation. So instead of that proportionality, we're going to go ahead and use K, which is going to be called our rate constant. Now, the rate constant right here is small k. Big K is for equilibrium constant, and as long as my temperature is constant, my K, my rate constant, is going to be constant as well. Now, when we go ahead and look at this expression right here, this is what we call the rate law. Now, more specifically, this is called the differential rate law. So you guys, we will talk about a different kind of rate law called the integrated rate law, but this is in the form of the differential rate law. So what we got here is K is our rate constant, and N is called the order that reactant is in. So basically what N is talking about is what is the impact of the concentration of A on the rate of our reaction. So another thing that you can consider N to be is the impact that particular component has in this reaction. Now here's the weird thing about the rate law. These K and N's, these are empirical values. So they are going to have to be determined by experiment. Now we can go ahead and run the experiment to figure out these values, but it is very hard to determine these things from the overall reaction. In fact, I want you guys to burn this into your head. The overall reaction cannot tell you what either N or K have to be. You have to go into the lab and do this experiment. Now, the order of the reaction, it can be positive, it can be negative, it can be an integer, it can be a fraction, all determined from our experiment. So let's go ahead and remember how our reaction proceeds. So again, here's time on the x-axis. Here is concentration on the x-axis. A is going to be our reactants that are decreasing over time, and B is going to be our products increasing over time. Now, what I told you guys was the rate is going to be the change in concentration of B over the change in time. And so if I were to try to put this on the graph right here, the change in concentration in B let's just pick two random points. These 2 points right here. This line right here represents the change in the concentration of B. And then this line right here, that's the change in concentration over time. Now, if I were to draw a line between these 2 points, so that right there, that is going to be the average of that rate at that between those 2 points. Now, if I were to pick any other point and draw a tangential line to that curve, that is what we call the instantaneous rate. And now this is going to be really important because if you guys take a look, all the lines that I draw tangential to that curve, well, they change over time. So what I'm going to do is I'm going to run an experiment called the initial rates method. Now, the initial rates method means that I'm going to go ahead and run a series of experiments that is going to help me determine this out for you guys. So this is going to be the initial rates method. And so let's go ahead and set up our experiment. Okay, so here's how we do the initial rates method. The first thing I'm going to do is I'm going to pick a place in our reaction where the backward reaction has very little impact. So a good thing to do is you start out with all reactant. If we start out all reactant, then we'll be at this place right here. We can measure our instantaneous rate there, and that is going to be the rate that we are going to look at. Now, to do this method, what we're going to do is we're going to run a series of experiments. So I'm going to go into lab. I'm going to run experiment 1. I'm going to note the concentration of my reactants, and then I'm going to measure the rate. Then the next thing I'm going to do is I'm going to run that experiment over again in experiment 2, but this time I'm going to change the concentration, and then I'm going to go ahead and measure the new rate that I get for experiment 2. Now, what I can do with this data is I can place this into equations, I can manipulate this data around, and then I'm going to answer these 3 questions right here. So let's go ahead and do this with the idea with these as our data set using the initial rates method. All right, ladies and gentlemen, let's go ahead and cover this out. And let's go ahead and answer point number 1, which was to determine the rate law. Now, I want the rate law in its full glory, but I can write down a very generic rate law, and that means that the rate equals some proportionality constant, or my rate constant K, times the concentration of HI raised to the power of N. Now, what I'm going to go ahead and do is understand that this rate law applies to each one of my experiments that I run. So what I can do is I can go ahead and write each experiment in terms of this basic rate law. So I can go ahead and say experiment 2, let's look at the data that was given in experiment 2. And so experiment 2, the rate that I found, 0.12. It has a rate constant of K that I'm trying to determine. And then what I have is I have the concentration. And this turns out to be 0.02 in this experiment. And I'm going to raise that to the nth power. Now, the next thing I'm going to do is I'm going to go ahead and write everything for experiment 1 in terms of the rate law. So again, my rate, 0.003 for this experiment. This is going to equal K. And in this time, the concentration was 0.01, and I raised that to the nth power. Now, what I'm going to do is I'm going to divide these equations one by the other. So I'm going to focus on my experiments right here, and I'm going to divide one by the other. And I'm going to see what that is. So I'm going to do this piece by piece. So 0.003 is going to go into 0.012 into 4 times. And so the next thing I'm going to do is I'm going to say K divided by this K is 1. And then I'm going to divide the next part, 0.02 raised to the n, divided by 0.01 raised to the n. Well, that's going to be 2 to the nth power. So note when I divide it, I'm just dividing section by section, rate by rate, K by K, and then the concentration by concentration. So this simplifies down to 4 equals 2 to the nth power. And so you guys can do this by inspection, that this is going to equal, or n is going to equal 2 to make that expression correct. And so what this tells us is now I can go ahead and write my rate law. Rate equals K HI to the second power. All right, let's see if we can go ahead and hit another point here. All right, so let's go ahead and try to do point number 2, which is calculate the rate constant. So again, I want you guys to remember that we did in point 1, we found that the rate equals K HI to the second power. And so now what I can remember is that each one of these experiments has to follow this rate law. So I can pick either experiment 1 or experiment 2 and plug in the values. So what I'm going to do right now is I'm going to plug in the values for experiment 1. Okay, so if I put in the values for experiment 1, what I get is 0.003 equals K, and this is to the 0.01, and I know that this is to the second power. Now, what I can go ahead and do is rearrange this. So this is 0.003 divided by 0.01 squared, and that all equals K. Now, if I go ahead and solve this, K equals 30. Now, what I didn't do right here is I didn't put the units in here. And I specifically didn't put units in here because I want to drive home this point. Small k right here, its units will change depending on the order of the reaction. So k's units are not something fixed here. So let's take a look at just the units in this equation. So like I mentioned before, rate up here, well, that has the units of molarity per second. And then molarity here, it has, so this is our concentration. Our concentration has the units of molarity, but you'll note there was a squared. So on the bottom, I have units of molarity squared. So what this means is that my units of K have to be 1 over molars per second. And so when I write my K, that is going to be my units for K in this particular reaction. All right, let's do the last thing, which is cover point number 3. So point number 3, it says calculate the rate when HI is 0.002 molar. Okay, so if that's the case, let's go ahead and write our rate law. And now we have the rate law in its full glory. The rate equals, and we figured out this is 30 per molar per second times HI squared. Now, if that's the case, let's go ahead and put in our values. So this is 30 per molar per second, and I want the concentration of my HI to be 0.002, and that's molarity, which is squared. And then if I calculate this out, this is 0.00012 molarity per second. And so this is going to be point number 3 on that slide. All right, so we've cranked out all this stuff. Let's go ahead and complicate matters and take a look at a more complicated reaction. So what we have here is a little bit more of a complicated reaction. In this case, what I have is not one reactant. I have NO and Cl2 coming together in this reaction. So this is going to complicate matters because what I want to do is I want to find the order to plug into my rate law. But what I need to have happen is I want to note that order means the impact of that particular reactant. So if I'm trying to find the impact of one reactant, I can't let the other reactant change. So in order to assess this, what I'm going to do is the same process I did last time, but I gotta make sure that if I'm trying to find the order of something, that I keep the other reactant constant. So in order to find the order of Cl2, I need to make sure that NO is held constant. And if I'm trying to find the order of NO, I want Cl2 to keep constant. This is going to require more experiments on my part. So in this case, what you guys will see that instead of running 2 experiments, I'm running a full 3 experiments. So let's go ahead and figure out all the details to this, and let's see if we can get a rate law out of this particular set. So I'm going to start this whole thing by writing down the basic rate law. So that means rate equals K, some proportionality constant, times one of my reactions, NO, raised to the nth power, times my other reactant, Cl2. And again, I don't know its impact or its order, so I'm going to raise that to the nth power. Now, what I'm going to do in this is I'm going to go ahead and find the order of Cl2 right here. So if I want to find the order of Cl2, I want an experiment where Cl2 is changing, but NO is remaining constant. So to do this, let's look at experiment 2 versus experiment 1. So I'm going to write down all the information here. My rate for experiment 2, 0.36. I have my rate constant, and now I'm going to put in my concentration. So this is 0.1 raised to the nth power. Now I put in my Cl concentration, and I see that my Cl concentration is 0.2 raised to the nth power. Now the next thing I do is I'm going to do the same thing and write the data for experiment 1. So we got 0.18 equals K. My NO does not change concentration, so 0.1 raised to the N, but my Cl is going to be 0.1 raised to the nth power. And again, I'm going to do the same thing. I'm going to do my division. So let's go ahead and divide these two things. So 0.36 divided by 0.18, that's going to be 2. K divided by K is 1. So 0.1 raised to the N divided by 0.1 raised to the N is 1. And then finally, on this block right here, 0.2 divided by 0.1 is 2 raised to the nth power. And so what I can do is I can simplify this all the way down to 2 equals 2 to the nth power, or m equals 1. Now that takes care of the order of Cl2. Let's see if we can go ahead and do the order of the other one, the order of NO. Now, I can't use experiments 1 and experiments 2. I got to use a different set of experiments. All right, so we're back here where we wrote down our basic rate law again. And so we're going to go ahead and look where NO is changing and my Cl2 is not changing. And so that is going to be experiment 3 versus experiment 2. So let's go ahead and write our data down. 1.45 equals K. NO concentration 0.2 raised to the nth power. This is going to be 0.2 raised to the nth power. Now we could put m in there as 1 since we solved it in our last exercise, but we don't necessarily need to do that. So let's do everything for experiment 2, 0.36 k to the 0.1 raised to the n, and then 0.2 raised to the nth power. Again, I'm going to divide these two equations up. So what I get is 1.45 equals 4, and then k divided by k is 1. 0.2 divided by 0.1, that's 2 raised to the nth power. And then finally, 0.2 to the nth divided by 0.2 to the nth, well, that is just 1 as well. So this goes ahead and simplifies to 4 equals 2 raised to the n, and then n equals 2. And so now what we do is we finally got our orders for each one of these. And so let's go back to our rate law. So our rate law now can be written. We found out that NO is second order, so we put it to the 2. Our chlorine is first order, so we can just raise it to the 1 or leave that out. Now, the way that we read this is we say that the rate is equal to our rate constant, where NO is second order and chlorine is first order. The overall rate is if you go ahead and add the individual rates up. So in this case, 2 and 1. So the overall order of this reaction is 3. This is a third order reaction. Now, I want to state something really important. Now, this is just a coincidence in this particular reaction, but you'll notice 2 and 1. What I want you guys to understand is the overall rate of the overall equation does not tell you the order, okay? This was just a coincidence that it happened to be that there's a coefficient of 2 in front of the NO and it became second order. This will not be the case in a lot of reactions. So be very wary that coefficients in the overall equation do not tell you order. Okay, so here's what I want you guys to do. This is going to be our second quiz. So what I want you guys to do is go through this set of data, and this set of data is for this hypothetical reaction. A plus B plus C gets me D and E. And now what I want you guys to do is I want you to go tell me what the order is with respect to our reactant A, B, and C. So there's going to be 3 questions that you guys are going to answer, and after you answer all 3 of these, we're going to go ahead and talk about the whole order of this thing. All right, let's do the order for reactant A. So for reactant A, I want A to be changing and everything else to be constant. And so if we look at that, that is going to be experiment 3 versus experiment 1. And again, it has to follow this rate law. So the rate equals K, A to the nth power, B to the mth power, and let's go ahead and C is raised to the Lth power. So let's go ahead and take a look at this. The rate is 12 equals K, and then my concentrations are going to be 0.2 raised to the N, 0.1 raised to the mth power, and then 0.1 raised to the Lth power. And then for experiment 2, experiment 1, our rate is K, for experiment 1, our rate is 3, and that equals K, and then our concentration, 0.1 raised to the nth power, 0.1 raised to the mth power, and then 0.1 raised to the Lth power. So if we go ahead and take this and divide these equations by each other, we get that that 3 goes into 12 4 times. K divided by K is 1. 0.2 divided by 0.1 is going to be 2 to the nth, and this is going to be times 1 and times 1, because anything divided by itself is 1. So this narrows down to 4 equals 2 to the nth power, so n equals 2. Now, we can go ahead and do the same drawn out process for our next guy, trying to find the order of C. Now, you can go through that long process, or if you are savvy enough, you can just take a look at the data and do things by inspection. You can just take a look at what's happening here. And so in this case, let's look at C. I need some place where C is changing. So that's going to be experiments 1 and experiments 2. And in this case, A and B are constant. And just by eyeballing it, what I can see is that I tripled the rate, or I tripled the amount, the concentration. If I tripled the concentration, let's take a look at what happened to the rate. Well, it tripled as well. It went up by a factor of 3. So if that's the case, exactly what I did to the concentration happened to the rate itself. So this implies that this is a first order process, and I can automatically say that without doing the long calculations. So in other words, if I doubled C and the rate doubled, I know it's first order. However, if I doubled C and I quadrupled the initial rate, then I know that it's a higher order. In that case, it would be second order. So in this case, if I tripled C and the rate went up 9 times, then I would know it's a second order reaction. But since it is doing exactly what I'm doing to the concentration, or the rate's doing exactly what I'm doing to the concentration, that means this is a first order process. So let's go ahead and take a look at the last one, which is what's the order with respect to B. So we can go ahead and work this one out. And let's just go ahead and do it the long way. If you guys want to do it by inspection, go ahead and try to look at it really quickly before I run through the actual calculations. All right, let's go ahead and figure this one out. So let's say rate equals K A to the mth power, B to the nth power, and let's do C to the nth power. And so again, we want to go ahead and make sure that B is changing. So that's going to be experiment 4. And I'm going to compare that to experiment 3, where B is changing and everything else is the same. So let's write down the data. 12 is our rate. K equals 0.2 raised to the mth, 0.2 raised to the nth, and then finally 0.1 raised to the nth. Now, let's go ahead and write the data for experiment 3, and you guys can see this is where you guys could have done it by inspection. The rate is the same. K is going to be the same, 0.2 raised to the nth, 0.1 raised to the nth, and then finally 0.1 raised to the nth power. Let's go ahead and divide those two equations up. And 12 divided by 12 is 1. K divided by K is 1. 0.2 to the mth divided by 0.2 to the mth is 1. And then finally 0.2 divided by 0.1. This actually gets us something. This is 2 raised to the n. And then finally, the last thing divided by itself is going to be 1 as well. So I simplify this expression to 1 equals 2 to the nth power. And the only way this works is that if n is equal to 0, so this is a 0 order reaction. All right, this gets us all the orders for our equation, our data. So we can go ahead and summarize all of this up. So this is the summary of all the data that we have. Our rate is going to equal k, a raised to the second power, b raised to the 0th power, and then c raised to the first power. Now, in general, if something is raised to the first power, we don't usually put the 1 there, so you guys don't have to put the 1 there. And then anything raised to the 0th power is always going to be 1, so we can simplify our rate law right here. And so what this tells us is it's second order with respect to A, 0 order with respect to B, first order with respect to C. So 2 plus 0 plus 1 gives us 3. So we've got a third order overall reaction. And from this, we can go ahead and calculate our rate constant K. You guys can do it on yourself, noting that any one of those experiments has to follow that rate law. So we can plug in those values and get that out there. Now, again, I want to remind you that this method is called the method of initial rates. And that means I'm running a series of experiments and I'm trying to get that instantaneous rate at the start of this reaction. And by changing one variable at a time, I can see the impact or the order of that reactant. All right. I hope that made sense, you guys, and I will talk to you guys in the next section.